Thanks everybody for showing up. What I'm going to do today is just present some of the work that I've been doing on predicting the impacts of climate change on Central American agriculture, and specifically this will be preliminary regional climate modeling results. This is the work that I've done for the past year and a half in collaboration with Alex Ruane. He's a civil servant here, and my NASA postdoctoral program advisor is Cynthia Rosenzweig, and then Richie Goldberg, who works at the Columbia University Center for Climate Systems Research. But in this building, he's done all the aggregation of the observational data, a little bit of which you'll see in the presentation. So just to give some context to the slides that I'll be presenting, there's been, over the last month, there's been extensive flooding in Central America. It's been a series of tropical depressions and intense low pressure systems, and this is just clearly an area that is susceptible to natural disasters that can have adverse effects on agriculture. And it makes it an important region to focus on, both in terms of current agricultural productivity and future agricultural productivity. So I pulled these images from the BBC. This is the Pan American Highway in Nicaragua, obviously flooded. This is some inundated areas south of Guatemala City. And then finally, most relevant to this presentation, this is a maize farmer. He's holding 2 damaged corn cobs. Tough to see because of the resolution of the image. But El Salvador has been especially hard hit by this flooding. And they're expecting to lose about 35% of their maize yields and 60% of their dry bean yields. And they're already seeing the impacts in the markets. Prices for maize have doubled within the last month. So clearly a region of interest for food security, both now and in the future. And so that's the status of Central America now. And of course, as with a lot of things at GISS, we're interested both in current climate and what's going to happen in the future in terms of both climate and its impacts on society. So this is just the standard hockey stick CO2 curve, just to motivate the fact that we're going to be dealing both with the present climate, trying to predict climate and predict agricultural yields, and then we're also going to look into the future and see how those yields are going to evolve under climate change scenarios.
Let's go back.
Sure.
You have emphasis on the left for nitrous oxide.
Yep.
On the right for methane.
Yep.
Where's carbon dioxide?
It's the red line, and this axis is the same. It's CO2 and nitrous.
So just million versus billion.
Except it's million versus.
Yeah.
Okay, fine.
Yep. So I've outlined a couple of key questions in agricultural climate change impacts. Before I came here, I worked on some regional climate modeling in the American Midwest. So these are kind of broad questions that encompass all of the research that I've done. First is, how well can we simulate space-time distributions of precipitation and temperature using regional climate models? This is the basic predictability problem. How well can we predict? Second, more relevant to the regional climate modeling aspect of things, we want to know the local response to precipitation and temperature to a warmer climate. So of course, global average temperature is useful for some particular applications, but when you want to look at food security, you need to know regionally what's happening to precipitation and temperature. And then this project in particular, we're going to start to try to look at extreme events. So this is a really difficult problem, especially given the state of both regional and general circulation models, but we're trying it. So we're looking specifically at droughts, floods, heat waves is what we're going to be looking at. We want to know the impacts of these changes in climate on crop yields, if any, and can we detect them, and what are they? And then finally, we want to know the key uncertainties in predicting climate and agriculture. So what happens in this system is you start with your general circulation model, you dynamically downscale it using a regional climate model, and then you use that regional climate model data to force an ag model, a crop model. And crop models, let me just do a quick sidebar. I'm not going to talk too much about them because we haven't gotten to the crop modeling aspect of this work. But crop models are just basically biophysical ag models where you give it T-min Tmax, precipitation daily, and you tell it what kind of cultivar you want to grow. You say, I want to grow, maize of this sort. You tell it when to plant. You give it its daily weather. You allow it to evolve. You fertilize it. You irrigate it if it's called for it, and then at the end you get yield, in tons per hectare or a similar measure. So whenever I talk about crop models, this is what I'm talking about. I'm not going to cover them explicitly. So you feed in. Yes, so the soils come, but we always assume static soils when we look into the future. I don't think we've ever changed soil profiles. Yeah, so the evapotranspiration comes from the Tmin, the Tmax, the RT, and then you can also put in winds to get the more sophisticated, beyond. I think the FAO method doesn't need wind, but if you want to go to like a Penman-Monteith, you need the winds. So you can also use the winds.
The model itself calculates the evapotranspiration.
Yeah, the ag model.
That's the Jim Jones.
Yeah. But as I was saying, so you have the GCM, you're downscaling it with the RCM, you give it to the crop models, so clearly there's uncertainties in each of the 3 columns. And then what's even more interesting is how the uncertainties propagate down the chain. So you have your GCMs. So one of the most interesting sets of questions is, what do we need to get right? So in Central America, if we don't get El Nino right, is the rest of it not even worth running because it's not going to turn out correctly? Or can we tolerate errors in El Nino, but we have to have the parameterization scheme of convection correct in the regional climate model? Will that give us the correct prediction? Or does everything get swamped by how much you fertilize the crop, or when you plant, or what cultivar you grow? So these are the questions that this research will start to get at, but of course you need to run giant ensembles and really take a statistical approach to get at these kind of questions. So those were broad questions. So how does this get applied over Central America? So we're taking a series of GCMs. Today I'm only presenting CCSM, the Community Climate Systems Model from NCAR. So we're taking a GCM. We're dynamically downscaling by 2 RCMs, RegCM3, Regional Climate Model version 3, and the Weather Research and Forecasting Model. And we're looking at the ability of these dynamically downscaled data to reproduce the current climate. So we do that by comparing to station observations at points. We do that by comparing to gridded observational data sets, which are at monthly timescales. And then for the years 2000 to 2009, we're going to be doing that by comparing to satellite precipitation products. So that'd be TRIM, CMORPH, and Persian. So we're looking at the current climate, our ability to simulate the current climate, and then we take that whole set of models, we run it forward into the future, and then we see how both means change and how extremes change and how variability changes. That's the overall goal. So just to motivate, I gave a couple images. This is the TRIM satellite being put together at Goddard Space Flight Center. This is the TRIM climatology if you plotted it for the entire world, or for its entire band, 1998 through 2009. And then finally, one of the facets of this research is to make sure that we make our findings accessible. So there's a joint partnership between NASA and USAID called SERVIR. And so they have nodes in Central America, in Sub-Saharan Africa, and in Tibet. And so what they are right now is they're basically like a regional climate center that does current geophysical hazard maps that they make available online. So right here, it's tough to see because of the resolution, but you have places where they have forest fires, earthquakes. This is all current. And then you also have this radar looking overlay, which is actually cloud top temperatures, which indicates heavy rainfall. So what we're going to try to do for them in collaboration is we're going to develop a climate change overlay that you can put on this. So where are extremes increasing? Where are extremes decreasing? What kind of temperatures can they expect?
This small question.
Yeah.
For clarification. Period 98 to 2009.
Sure.
presumably included some El Nino events.
Correct.
El Nino years. How is that embedded in there, or?
It's just average. So whatever, this is observation. So whatever happened was, it's just the satellites, whatever the satellite senses what goes here.
These are anomalies that can disrupt the normal situation.
Right.
So,
This is just long-term average though. There's no, this isn't deviations from,
an 11-year average.
this is, yeah, just an 11-year average.
Would you see big differences if you took the El Nino periods out?
I haven't looked at it, but I would assume that you would.
There, you know, an 11-year period isn't so much to give us a great statistical sense of El Nino, but you can certainly get some of the big events, you know, El Nino minus La Nina, and see what the teleconnections are.
Yeah, Alex has actually done some of that preliminary work on that, but I haven't actually looked at it myself. Okay, so before I jump into the few figures that I have, I just want to give a brief overview of the numerical models that I'm using. I don't know how familiar everybody is with the different types of tools that we use, but I figured I'd start at the bottom and build it up. So basically, we're using the crop models, which I'm not really going to cover. Most of it's going to be talking about general circulation models and regional climate models. So your GCMs, I assume most are familiar. You just have mass, momentum, energy on a spherical surface. You set them, you run them forward, they predict climate for you perfectly, right? They're global in spatial coverage, but they have a coarse resolution. So that's their limitation, coarse resolution. That's why we come in with regional climate models. They're limited in their predictive ability. So you need a GCM on the outside. They need to be forced at the boundaries, but they give you that fine spatial and temporal coverage that you want for impacts type work, like agriculture. So just to kind of visually represent this, I took an image from the MODIS instrument of NASA's Terra satellite. And so this is the full image. So I think it ends up being 5,400 pixels across, 2,700 pixels up, down. And I aggregated it to a standard GCM resolution. So this is 2 degrees by 2 degrees. So I just averaged, so now you're 180 across, 90 up and down. So if, of course, this is not scientific in any way, but it's just a visual representation. If models were perfect and all you were dealing with was averaging, this is what you would see. And then this is a standard RCM resolution. Actually, it's a little bit coarse. This is 1/2 degree by 1/2 degree, so it's 720 across, 360 up and down. And that's kind of the detail that you pull back when you use a regional climate model.
We don't see any difference.
You don't see any?
I can.
Okay.
The middle looks, I mean.
Well, let me blow it up for you. Okay, so this is our full image at full resolution. This is how we wish we could predict the Earth system, and you know, with perfect information. This is what we end up doing. So we have our GCM over the entire world, and then over our area of interest, we run a regional climate model with high resolution. And so this is our region of interest, which I'm going to launch into right now. False. I'm going to go back and show you what's inside of a regional climate model. So, because I wasn't sure how familiar people were with regional climate models, I just wanted to give a brief introduction to what one would look like if you broke it open. So, this is RCM3. We're also using WRF. But as you can see on the outside, you have your coarse grid boxes. That's your large scale. Those are your boundary conditions coming in. They can be anything, really. NNRP2, this slide was for some old work, so it's ECM5, CCSM, GISS MOLE, whatever can sit on the outside is fine. And then inside the regional climate model, for every set of climate physics, you have an associated set of equations or parameterization schemes. So you have atmospheric radiation, you have your large scale precipitation, so frontal systems. You have your PBL, convective clouds and precipitation. You have multiple parameterizations of that because it ends up being a very tricky problem. Sea surface temperatures, which actually come in from the large scale forcings. Regional climate models don't have a dynamic ocean model unless you're told otherwise, unless somebody has explicitly linked one like ROMS to it. Ocean flux parameterization, that'll just give you your latent and sensible heat fluxes. And then surface physics, there are a couple of options in RCM3. We chose actually the simplest, BATS 1E, but it doesn't give bad results.
Which ocean are you talking about? There's two bodies of water
Right.
in Central America.
Both of them.
Contrasting, and both have
Both are being
fluctuate
fed.
back and forth.
Both are being fed by the sea surface temperatures from the large-scale boundary conditions. So in all of the simulations I'll present, it's all CCSM surface temperature.
So do you keep getting feedback from the GCM as you evolve this in time to make sure the boundary conditions stay consistent, or do you just start out with the global GCM to set your boundary conditions on your regional model and then it evolve on its own?
They run parallel.
They do.
So the GCM runs forward with boundary conditions as the RCM runs forward. Yep.
The GCM does not feel the
GCM does not feel the effect of the regional climate model. So it's just a.
So but
I
it's
think
sort of
it's
like resetting the boundary conditions every time step.
It is. It is. No, it forces it back to. It doesn't allow. It's not a unique.
It's not an additional.
It's not allowed to drift as far as it wants.
Okay.
But just to briefly,
What's the
take a
reason?
sidebar. You do crop out the outside, so you're not.
There's a buffer zone.
There's a buffer zone that kind of eases it in, and then you crop out the outside.
So it's
you're
kind of
not.
like a relaxation.
Yeah, it's an exponential relaxation into the.
But
into the
internally, it's initialized at the beginning, and then the sea surface temperatures are cast, or the sea surface temperatures are given by the large scale. That's the only kind of internal, inside your domain.
Right, inside your domain, the sea surface temperature is the only thing that evolves outside of the physics of the regional climate model. But outside your domain, you're getting pushed by the GCM.
I'm still bothered by the fact that there are two seas.
there are two. This doesn't show. This is representative. This is not Central America.
This is general.
This is general.
This is a cartoon.
Okay, so this is the numerical experiment setup. Everything in green is run, and you'll see today. Everything in yellow is ready to go. Actually, been run before, but has to be rerun for various reasons. And then everything in red, which you don't see, is because it's just too big. It fill up the entire slide. Because we have a lot more to do that we'd like to do. Okay, so RedCM3, and this is just the parameterization scheme. We don't really have to pay too much attention to this, but we ran it with NNRP2 for 1980 through 2009, CCSM for the control period, CCSM A2 scenario, and then we're going to run it for the B1.
Briefly, what is NNRP2 CCSM?
NSEP DOE reanalysis. CCSM is the NCAR Community Climate Systems model, and then the A2 and the B1 scenario of that. Yeah. Feel free to jump in. Sometimes I skip through things that. Yeah. We're going to run with a different parameterization scheme, which is pretty straightforward. We've run with WARP, but we got to rerun because we're doing some different time periods. And then, off this chart, we need to use more GCMs because CCSM is just, you can't bound yourself with one GCM. Because as you can imagine, because you're forcing it as you move forward, your GCM has a big impact on what your final solution is. It's
So
a
you see
blend.
differences when you've tried different GCMs, or you know they will exist and you want to see these later?
I know they will exist because I've done other climate, regional climate modeling over like the American Midwest with different GCMs. But over this, we've only used CCSM so far. But you can see the difference because we use NNRP2 and CCSM, and you'll see the difference between the two. Okay, so we'll be presenting the three green simulations today. Okay, so here are what our results look like. So you're looking at 1980 through 2008. So this is RegCM3 driven by NNRP2, so the NSEP DOE reanalysis 2. This is RegCM3 driven by the NCAR Community Climate Systems model. This is University of Delaware precipitation. So this is observed on a half-degree grid. That's why it's a little coarser. This is your color bar. I didn't put them on the other two, but consistent color bars for all the figures. So you're comparing apples to apples. So what you can see is, it's a long-term average. So you're picking up some of the signals, but I can say the American Midwest was much easier to simulate. It's difficult to get precipitation right in Central America. But you do get some of the gradients being picked up down here in the observations. If you move to CCSM, you can see it's much drier. You're not picking up nearly as much rainfall where you should be, and it's really kind of a wasteland over in Colombia and Venezuela, whereas in the observations in an NNRP2 you do see some precipitation.
Question.
Yeah.
Was it for the same hypothetical climate conditions, or was there a difference?
No, same. So all this is control. So 1980 through 2009.
Because in a previous slide, I think there was some indication that we were modeling sort of different concentrations of carbon dioxide.
Yes. So with the climate change scenarios, those will be different. But these are all for the control period. So this is reanalysis, observations, and GCM. All these two are downscaled by the regional climate model. This is of course just observations. Okay, so that's what precipitation looks like. Luckily temperature looks a little better because we always do better with temperature. You can see it's picking up the topography, which is nice, at least. If you look at Honduras and Nicaragua, you can see it's a little cool in both the models. That seems to be a regional climate model phenomenon because it's not getting picked up by either large-scale forcing. You can start to see some of the differences between the large-scale forcings. Like if you look at CCSM, much drier, much hotter down here, whereas if you stick with NNRP2, it's cooler in Colombia and Venezuela. So that's the overall picture when you look at temperature. So again, these are long-term means. This is a subset of the full analysis that will be done. So this is using gridded observational data. We'll also do 2000 through 2009 with satellite precipitation products. And there we can look at both the climatology, and then we can start to look at some statistics for extreme events, like the percentage of rainfall over that entire 10-year period that falls in the 30 rainiest days, things like that. So we can start to tease out some of the extreme kind of statistics that we can hope to see how well the models do. And again, we want to run with additional GCMs to see if we can get better representations of the climate, basically. Okay, so those were the 2D figures that I'm going to show. Now I'm going to hone in on one particular site. So the crop models that I was talking about, those are point-based models. So you run them at a particular point. So what we're going to do now is we're going to focus in on Los Santos, Panama. We have observational data for that site. We have good observational records. We're going to run crop models there. So we want to see how well regional climate models do in simulating that temperature and precipitation. Background here, you have
observational models. You mean precipitation, temperature, and crop yields? What do you mean by observational data?
Yeah, so observational data. Yeah, we have Tmax, Tmin, and precipitation, which turn out to be what crop models need as inputs. And then crop yields, we might have some. We're working on crop yields.
You're really close to the Darien Gap, where you showed earlier you had absolutely no data.
Where is this?
The Darien Gap, which is between Colombia and Panama. You had no observational data in the previous slide, but here.
Oh yeah, so these are drawing from different observational data sets. So this is
right. You see that
this
gap
is
down
yeah.
there?
So this is the Wilmot Montsura University of Delaware data set. So this is a gridded half degree by half degree. When we go to this stuff, when we go to a particular site, that means we have a station on the ground, and we've gotten the data set from it.
And that's on the Pacific side.
Yes. Yeah, this side. Yep. And background here, this is just maize in tons per hectare. This is a global data set by Manfreda et al. Just showing general yields of crops. It's global. It's through remote sensing and survey, but it's kind of covered by the red star. But there is some green down here, so it's a place where maize is grown, and we have observational data for it. Okay, so what I'm
stereotypes. I thought maize was grown everywhere.
Okay, so what I have plotted here is we have a seasonal cycle. So you have 0 through 365 days. So I took the whole control period. So that's 1980 through 2009, stacked it up and averaged down the year. So this is a seasonal cycle. We have 2 meter maximum temperature, 2 meter minimum temperature, and precipitation. These are what the crop models take. These are the inputs to the crop models. The blue line, that's NNRP2 downscaled by RegCM3. The red line is CCSM downscaled by RegCM3. black line is observations, and then your long-term average is up in the legend. And so what you can see is that CCSM overpredicts maximum temperature and imposes a seasonal cycle that's not really there. Oh, I knew 30-year smooth. That's why it's so smooth. It's 30-day smoothing filter on it. That's why it's smooth. So you can see, yeah, CCSM overestimates and imposes a seasonal cycle. NNRP doesn't do too bad. I mean, it does overpredict, and you're talking about temperatures in the range of 4 degrees Celsius, which isn't great, but it does capture the shape, and it's better than CCSM. Minimum temperature, notice how fine the scale is. Actually, the models do a reasonable job with minimum temperature. So they're both under-predicting minimum temperature, so CCSM clearly has too much variability in this diurnal temperature range. NNRP2 is more consistent, but they both underestimate minimum temperature and don't really capture the shape. NNRP2 better than CCSM.
Why do you think these models are better and more similar? What do you think the reason for that?
Well,
I'm not saying you have to know it. I'm just
yeah.
curious.
I mean, it's a good question. I think it's easier.
4 degrees centigrade is a huge amount.
I think it's easier to predict at night because all you have to do is basically predict the decay of temperature. Whereas during the day, you have to get the clouds right. You have to get the soil moisture right because you're looking at 2 meter temperature. So you're just dealing with a lot larger. You're just dealing with a lot larger source of energy here, and you're dealing with a lot larger range. But
and I'd add a couple. I mean, the seasonal cycle in this area is not very strong, and a lot of it is just the ITCZ, meandering up and down, and that it's difficult for that to be seen inside the regional model. This is basically an organized band of convection that has to fall in the right spot.
Intertropical convergence.
Yeah, the intertropical convergence zone. So it's that T-min, with the narrow band. A lot of people basically consider this a very low seasonality, except for the precip.
Yeah. Okay, and then so if we go down to precip, you see NNRP2 overestimates. You saw it. I mean, these often pair together. So when your model is dry, it's often hot. So this is consistent, but you have CCSM underestimating. NNRP2 kind of captures the bimodal seasonal cycle that the observations show, but it overestimates significantly in terms of precipitation. I mean, it's a large overestimation of precipitation, but even over the American Midwest, we don't do great on precipitation. I mean, it's bigger than what we would see over an easier domain to model, but it's not out of the range of what's seen.
And this is, once again, over a period of?
This is over a period of 30 years. This is a 30-year average.
Another thing maybe just I'll mention there is that the black line on the bottom is observations, right? So
black line in the middle.
Yeah, in the middle. Yeah, on the bottom of the panel. So there's the first peak of rainfall, and some farmers are able to plant a maize crop then. And then they harvest in that midsummer dry spell, and then the main growing season is actually that second peak. So for the models to be doing better on that second peak means we have a better shot at the agriculture that's going there.
And during this 30-year period, there have been several anomalies.
That's correct.
Anomalous years of El Nino and La Nina fluctuations.
That's right. And so.
And that's all somehow or other composite.
I mean, it's all just straight averaged into things, which I mean is a good question, which is why we then go and look at the PDFs of temperature and precipitation. And this is just an example. There's going to be a more sophisticated analysis done. But here, all I've done is taken maximum temperature, minimum temperature, precipitation. Again, daily data for that whole 30-year period. I've binned it, at certain points, and then we just look at the PDFs, the histograms, the distribution. So you can see for the maximum temperature. Again, you can see CCM is too warm, NNRP is too cold. They both have a larger distribution than what the observations show. Minimum temperature, things really start to collapse. I mean, it because you don't have that extended, y-axis. So the models do a reasonable job, but of course they're not getting things quite right. They need to be shifted and a little bit more broad of a distribution. And then finally, you have precipitation. So you can see NNRP2 just overestimating significantly across the board. They have observations are in the middle here. You can see CCSM actually doesn't do a bad job with precipitation when you look at it as a PDF. It's just missing a lot. It's just missing a lot of the low precipitation events. And just a note on the precipitation, I did cut out. There's a giant bar that sits over here with 0 precipitation, but I cut that out so you could see, just the low precipitation events and things. Yeah.
So this NNRP and CCSR is different GCM, right?
So NNRP2, that's insecurity reanalysis. CCSM is a GCM, and they're both RegCM3 downscale.
Okay.
And
so
that's what you're seeing up here.
yes, does it like a boundary is the only difference? Right?
Yeah, the boundaries are exactly. The boundaries are the only difference.
But then their results are very different.
The results are very different.
So I was wondering whether I guess this would be like a free GCM simulation. It's not with the real analysis. Yeah?
That's right. The GCM is just allowed to
So the
evolve.
question is how the free run is good. I mean, compared to the real
Yeah.
analysis. Have I ever done any?
Yeah, so that's a good question. So what should appear, if it didn't make it too busy, what should appear on a separate set of figures that also get presented is the GCM raw data for, for temperature, for Tmax, Tmin, and precipitation. But of course, one of the problems with that is you'd have to pull daily GCM data for analyses like this. But definitely in the monthly and the seasonal cycles, you could pull GCM data and show it on there, and to show how the GCM itself does, and then it would give you some ideas of what errors are being created by the RCM and what errors are coming from the GCM. And then also if you had if I was showing you multiple RCMs, you would get some idea of where the inaccuracies were within the models. Yeah?
So, a few questions. So, how far away from the boundary is this location? So, how did you choose the size of the regional climate modeling domain? And finally, in some regional models, at least the ones I've used,
Yep.
you can sort of gently nudge the regional model in its interior using, some things like geopotential height
Right.
from the host's data set. So those
Right.
three questions in one.
Okay, so Los Santos sits about here, and then this is not the full domain. So this is this is 5 points on each side cropped off the full domain. So 5 points times, it's a 30-kilometer resolution run, so it's about 150 kilometers in on each side. And then we make sure we're on the interior of the domain when we.
But still, maybe that's not large enough. I mean, if the regional climate model domain were bigger, then you would be seeing more of the precipitation field would reflect more of what the regional climate model wants to do physics-wise.
That's true.
Over the oceans, especially at low elevations, if you are convecting an air which is too dry, sort of hypothetically, your regional climate model may be able to recover from that over some distance. Distance is long enough.
You're absolutely right in the fact that if you if you expanded out your regional climate modeling domain, you would change the interior solution of the RCM. I would argue that you're not. The GCM I think the layer over which is 10 points. So I'm showing 5 points that are being touched by the GCM explicitly, but it's an exponential decay. So by the time you get 5 points in, there's almost no solution in here that's being significantly impacted by a GCM. And you can make your domain, but it's a balance of how many runs you want to do, because the bigger you make your domain, you're at 30 kilometers, so it scales.
Speaking, the winds were all coming from the northeast, then your site would be well in the interior without
Right.
between the Pacific side and the Caribbean side. And so speaking of the interior, it's very introduces an entirely different set of conditions.
Why did you pick this size, I guess? Maybe.
So this size is a blend of computational efficiency and including everything within our domain, but staying far away enough from each of the points that we are interested in, so that you weren't, trying to, because regional climate models it's pretty much garbage on the very edges, because you're getting that interface between the GCM and RCM, and you don't want that in your solution. So after cropping, it needs to include all the major points that you want to look at. It needs to not crop particular features, so you want to give it a little space on each of the oceans to allow there not to be any shocks in the system. I mean, it's a blend of multiple things. And I mean, you can make the RCM solution as big as you want, but you just drop your ability to run a lot of simulations. And to answer your second question, it's not a spectrally nudged model, so it doesn't receive any information in the interior from the GCM besides what's given at the boundaries and propagates inward.
A couple of things I might mention here, which is that this domain is notoriously difficult because it breaks a lot of the kind of standby rules of what you'd like to do when you're setting up a domain. So in general, you don't want to have the edges of your domain go through major mountain ranges, but there's no way of avoiding the Andes. And then you also, would prefer not to have strong kind of convective regions like the intertropical convergence zone, which runs right smack through the middle of this. So basically, 3 of our boundaries are in trouble right from the start when we're looking at this region. And it's one of the reasons that what we're trying to do with this project is not necessarily, we're trying to do our best in terms of hitting the climate, but the real questions we're asking this model are about how things change. So what we want to see is, for example, how the interior versus the Caribbean coast versus the Pacific coast might react. And a lot of, I think, what you're getting at is, whether the weather comes from the Caribbean or the Pacific side makes a huge difference. And I think as we look at the seasonality, we might see that when it's coming off the Caribbean, maybe it's doing well. When it's coming off the Pacific, maybe not. So those are the types of things we can start to inquire.
Yeah. And there are, of course, a whole set of games you can play after you run your regional climate models to bias correct, to get them into reasonable alignment with observations. These are just, we're giving you the straight RCM results off the model. Okay. So preliminary results in next step. So I didn't really mention this earlier, but we're running our future climate is 2020 to 2050. I didn't present any of those results yet, or I won't present any of those results today. Our control period is 1980 through 2010, and this was done because farmers, because this is being an ag-focused project, farmers are interested not in the end of the century as much. Their decision horizons are much smaller. So this is kind of a blend of what we want and what the ag modelers want. So we kind of knew this going in, but preliminary results, we're probably not going to be able to detect mean and variability shifts in precipitation and temperature between these 2 simulations, and you saw exactly why. You just have large biases that are going to swamp anything that you see in terms of a climate change signal. And then also the large-scale forcing appears to play the dominant role in the simulation of regional climate.
It's a missing word there.
Where?
After dominant.
Okay. Oh yeah, roll. Should say roll. And then, so next steps, we're going to evaluate NNRP2, CCSM, and GCMs over Central America. So that was looking at the large-scale forcings themselves. Assess 2000 to 2009 precipitation using TRIM. That's trying to back out some of those extreme statistics. But again, we only have the decade to work with because that's really the satellite era over which you can get reliable satellite precipitation. Deploy and calibrate the crop models at 4 pilot sites. So Los Santos is one of our pilot sites, and then we have another one for maize, one for rice, and one for dry bean. And then because we're probably going to have to move around, being able to predict directly the difference between, 1980 through 2010, 2020 through 2050, we're going to construct sensitivity tests to explore decadal variability. And along here should also be a more in-depth atmospheric analysis. So along the lines of what he was alluding to, you have to look at geopotential heights, winds, see where your models are getting it wrong and for what reasons. So that was really the end of the research that I wanted to present today. I'm just going to run through quickly 2 other projects within our group that I thought I'd highlight since I had the stage. So we have the Agricultural Model Intercomparison and Improvement Project.
Jonathan?
Yeah.
Can I say one more comment on
Sure.
your next steps? So if you compare to trim data,
Yeah.
the problem with trim is that it has an overpass, I don't know, somewhere in the morning or so. So it's not daily precipitation, but it's instantaneously.
Right.
So and that's a problem if you compare it to basically data, daily model results. So I'm not sure what the diurnal cycle and so is in this region, but it can get you into problems, I think.
Yeah. So I guess the idea here would be that we'd have to look closely at the diurnal cycle and see if we would
I think
see a bias, maybe average over a week instead of daily.
No, it's actually not so much. There's some trim products. I think really is what we're like. You mentioned trim and Persian and CMorph, and those are actually a combination of the microwave trim type imaging and some of the geosynchronous satellites looking at the IR. So they actually have continual coverage.
Okay.
So basically, the idea is they've done a really nice algorithm connecting the IR to the overpass, higher quality data.
Okay.
So you can actually get 3-hourly results.
Yeah, doesn't trim have 3-hourly results itself?
In the product.
Yeah, okay, so the trim products is what we're using. I think it's 3B42.
Okay.
Yeah. Okay, so I just wanted to highlight 2 projects that are in our group. This is being led by Cynthia, but Alex is the science coordinator. The Agricultural Model Intercomparison and Improvement Project. This is sort of along the lines of the work that I was presenting. It involves looking at climate now and in the future and prediction and predictability of agricultural yields. So it's a large project, it's global, and it looks at food security under climate change. It's ourselves, we work with USDA, we work with the University of Florida, colleagues there in crop modeling, we work with colleagues at Oregon State University in economic modeling. And basically it's a 2-track approach, so the first track is really a model evaluation and intercomparison, so it tries to bring some of the more rigorous model intercomparison that goes on in the climate modeling community through like CMIP5, Cordex, NORCAP, things like this, to crop and ag econ models because it's just sort of been missing up to this point. So it's basically just taking historical climate predictions, running them through a suite of crop models, so an ensemble, so you can compare the crop models, a suite of ag econ models, so that you can try to produce current food production and evaluate and intercompare the models. Track 2 is future climate scenarios, which we're in the process of generating. This again gets run through the same set of crop models and agricultural economic models. These are trade models. To give you future agricultural production, food security, changes in food prices. And then there's a large adaptation, mitigation, and extensions component, and we're also, we have money from UK DFID to work with collaborators in sub-Saharan Africa and South Asia, and they'll be doing some of the crop modeling and climate modeling and ag econ modeling work in their regions. So that's about all I can fit into a minute introduction of AgNet. But it's a big project with a lot of great researchers and a lot of great research going into it. There's a water resources component. There's uncertainty. There's scaling issues that are pervasive, going from point-based crop models to regional economic models. It's a lot of work. And then finally, the other project that I would say is one of the larger projects in our group is CC Run, and this is again one of Cynthia's projects. Radley is really the lead on this, and it focuses on water, coast, and health in the urban northeast corridor. So that's Philly, New York, and Boston. So water, that's water delivery, wastewater. Coast, that's basically flooding, and then health, which is air quality, heat waves, which is being done in collaboration with some researchers up at CCNY. And then it deals specifically with city issues such as urban heat islands, the air quality, coastal development, the mess that is the institutions around here, and highly diverse socioeconomic communities. And with that, I'd be happy to take any questions. Collaborators, Alex, Cynthia,
This is very
versions of the RCM3?
What'd you say?
The different versions of the RCM3, I mean, you focused on one particular version, but what are the degrees of freedom? Did you have options to use?
Yeah, there are options. So in we're going to run another set with a different convective parameterization scheme, but that's probably as far as testing the internal variability of the model as we're going to go. I don't think the surface physics scheme is worth changing, and I don't think it's worth trying to mess with parameters too much.
What convection scheme is in there now?
So right now it's the Grell with the Fritz Chapel closure. We're going to try the Quo. Once you have it set up, it's pretty straightforward to run the extra convective schemes.
You haven't tried that yet.
Haven't tried that yet. No.
But it brings up a good point, which is that increasingly people are going to ensemble approaches for these. So the Cordex project that Jonathan mentioned is the coordinated regional downscaling. I know you're involved in, trying to set up domains around the world. And when we started this project, there was kind of no hope of that in Central America. And just to get more than one RCM would be a huge improvement for that area, just to start to look at where the biases are coming from. But as we're going forward for the AgNet project and elsewhere, we're going to be looking at ensembles of different RCM, GCM combinations so we can get a feel for different sources of uncertainty.
I mean, it's the disk space and the time to run it, and then for pulling in multiple large-scale forcings, it's the time to write the code to ingest, because you have to prepare the boundary conditions so that the regional climate model can read it. So
But even those ensemble projects are not run by one group at one place. It's distributed. Everybody runs their own model and contributes, which is really the best way to do it.
Yeah. Versus trying to take it and pour it yourself. Yeah.
You guys mentioned that you ran some more fronts but need to rerun them. Do you guys have the ability to feed pre-processed GCM data into the warp?
Alex can speak to that.
So
he's running one.
Two of those boxes I would have put green for me. The future runs were
Yeah, the future runs are done.
I originally ran 1970 to 2000. We decided to move to 1980 to 2010. So that's why we reduced some of the baseline. But that was a nightmare of pre-processing that we had to do.
And you have that ability.
Yes, it's a mess.
GCM.
Yeah, I mean, amazingly, WRF outputs, or they put out their output in netCDF, but they can't take in netCDF, which is just a little ludicrous. And so I had to unpack the WRF intermediate formats and recreate them independently from the netCDF CCSM. Okay. I've tried to block out that memory, but I do have all the files.
Isn't there the option to run WRF in global mode and also CM3 can be run in global mode?
I know Red CM3 is not able to be run in global mode.
But CM3 is
CCM. Red CM3?
WRF can be run in global.
WRF can,
But it's
Red
it's
CM3
it's
cannot.
I thought Red CM3 comes from UK.
Comes from MM5 originally.
Maybe headcm3.
Yeah, I think.
Yeah.
But maybe this might make it simpler to take the global model up and adjust it to the original model. It's the same model. And the shock at the boundaries may be
Yeah.
less.
About that third picture, we land safely without falling off the plane.
Yeah, that's from AMS last year. Some quality.
The illusion is fantastic, though. I'll just take the 10 seconds to plug that AgNet project. We just had 110 people from 30 different countries at a workshop in Texas. Jonathan mentioned the UK DFID money. They're substantially funding the kind of core part of the project. And too often in the past, when people have looked at impacts of agriculture, they've taken hopefully several different climate scenarios, but then one crop model, and then probably didn't even get to the economics. So we're establishing, this kind of is the framework that we think needs to be done for, you could replace crop models in ag econ with ecosystem models and ecosystem economics. There's a lot of different things you can put in there, but this is the general framework, and it is not strongly established in a lot of the impacts community. So we've actually been able to get the leading crop modelers and ag econ modelers to buy into this approach going forward, and we think this will be one of the highlights of the kind of working group too going forward. So we have great confidence coming from the leadership of those teams.
None of you have great confidence if you're piggybacking uncertainty upon uncertainty.
Well,
And what's the reality?
I said that the great confidence
in one's lifetime.
Yeah. Well, the great confidence is in the approach being the right approach. The uncertainty cascade is immense, and most people have kind of just tried really hard not to look at it, and I think we are trying to look at it. So we have a whole working group on uncertainty, and I think one of the biggest contributions, in the first couple of years that we're working on this project is going to be to recognize, one of the things we want to look at is the cascade, but also are there bottlenecks? Maybe one of the things we're also doing is we're taking those, let's say the trim products, right? There's at least 3 that we work with, and the question is, are they chasing precision that we don't even really need, because when you actually go to apply those, things, the difference between one or the other, the crop model doesn't even care. So we're trying to figure out whether it's the climate information that's holding back this process. Maybe it's the crop models don't handle CO2 or the nitrogen or some of the cultivar genetics about how things are grown. And then, our economists love to say, give us any crop model result, give us any climate change result. We'll just change the size of our farms and wash all that away, because some of the development and agricultural sector investment is the biggest piece of that puzzle. So just kind of building this framework and starting to put numbers on, and error bars on things. I don't think we're gonna get to the end and say here's our precise solution, but we're at least trying to establish a framework that could point to the problems.
We'll make the crop modelers or climate modelers look good.
Yeah.
Shake some responsibility.
Well, but the big thing that gets back to Jonathan's thing here is that also when people have done a lot of these assessments, they've just taken mean changes. They often haven't even taken growing season mean changes. They've just taken annual changes and applied it into their crop models. So we think that's not good enough. We think focus on when the crops are actually grown, and we want to have mean and variability changes. So our prime interest actually in the RCM results is to ask some of the questions about local, high resolution topography, kind of complex topography feedbacks, coastlines. Some of the shifts in the distribution of events are the types of things, the GCMs can tell us more about the mean changes than the RCMs in a lot of cases, but when you actually want to talk about the changing mesoscale dynamics in a moister environment or a more energetic environment, you need to have these parameter stations to do that. So I think we're always saying we're running these regional models because we have real questions for them. We're not going to take those RCM results and plug them straight into the crop models because we don't trust them that far.
Really, you should give a talk on this slide.
Oh yeah, I think I've been meaning to sign up for the lunch. But no, this is a
I
big
think
thing.
you have people who could probably sign you up right here.
Yeah.